Module 2, Frequency Response, Feedback, and System Stability. 2.1 Frequency Response of Amplifiers. Amplifiers do not behave the same way at all frequencies. The gain of an amplifier varies with frequency due to the presence of capacitive and inductive elements. At mid-band frequencies, the amplifier gain is approximately constant. At low frequencies, coupling and bypass capacitors reduce gain. At high frequencies, transistor capacitances and wiring inductances lower gain. The frequency response of an amplifier is often displayed on a Bode plot, which shows gain and phase as functions of frequency. This allows engineers to see the bandwidth of the amplifier and its ability to process signals of different frequencies. 2.2 Analysis of broadband and narrowband amplifiers. Broadband amplifiers are designed to work over a wide range of frequencies. They are important in applications such as audio systems and video amplifiers. Their design focuses on maintaining flat gain across the band of interest. Narrowband amplifiers are optimized for a specific frequency range, often around the carrier signal in communication systems. They typically use tuned circuits with inductors and capacitors. Understanding whether an application requires broadband or narrowband amplification is a key part of circuit design. 2.3 Communication circuits. Amplifiers are fundamental building blocks of communication circuits. In radio receivers, for example, low-noise amplifiers boost weak signals from the antenna. Intermediate frequency amplifiers select and strengthen signals at a fixed frequency. Power amplifiers drive the output stages, such as loudspeakers or transmitters. The ability to design amplifiers that handle signals accurately and efficiently is therefore central to communication technology. 2.4 Feedback in amplifiers. Feedback means feeding a portion of the output signal back to the input. Feedback can be positive or negative. Negative feedback is widely used in amplifiers to improve stability, reduce distortion, increase bandwidth, and control gain. Positive feedback is less common in amplification but is essential in oscillators. The effects of feedback on amplifiers include reduced overall gain but improved accuracy, increased input resistance and reduced output resistance, improved frequency response and reduced noise. Feedback is one of the most powerful tools in electronic circuit design. 2.5 Analysis of feedback amplifiers. Feedback amplifiers are analyzed by studying how the feedback network interacts with the amplifier. Important considerations include loop gain, the product of amplifier gain and feedback factor. Closed loop gain, the gain of the system with feedback applied. Effect on input and output impedances. Trade-offs between stability, bandwidth, and distortion. By carefully designing the feedback network, engineers can tailor amplifier performance to meet precise specifications. 2.6 Stability and compensation techniques. One of the risks of feedback is instability. If feedback is not properly managed, an amplifier can oscillate or produce unwanted signals. To ensure stable operation, engineers use compensation techniques such as adding frequency-selective networks to control phase shift, using dominant pole compensation to ensure stability at high frequencies, adjusting loop gain to provide adequate stability margins. Stability and compensation are critical in high-performance amplifiers and communication systems, where reliability and accuracy are essential. Module 2 Summary. In Module 2, we examine amplifier frequency response, broadband and narrowband amplifiers, communication circuits, the role of feedback, analysis of feedback amplifiers, and stability and compensation techniques. These concepts build on the fundamentals from Module 1 to give a complete picture of amplifier design and application in electronic systems. Course conclusion. We have now completed the course Applied Electronic Systems. Module 1 covered the fundamentals, amplification basics, amplifier classification, transistor biasing and stabilization, small signal representation, and analysis of single and multi-stage amplifiers. Module 2 extended this knowledge to frequency response, broadband and narrowband amplifiers, communication circuits, feedback, and stability techniques. Together, these modules provide a strong foundation in both the theory and practice of amplifier circuits, preparing you to analyze, design, and apply electronic systems in real-world applications.